you would start the design process of most electronic or electric circuits. You'll start off at the schematic phase, drawing a schematic, and then using some sort of simulation software to verify your results before carrying on with your design. So, I mean, simulation is a very, very, very useful tool, and it can highlight some design faults that we might have in our circuits. Now, in EagleCAD, it's a really good, well, it's an okay simulation environment, meaning that we can simulate some circuits, at least RCL, resistive, capacitive, inductive type circuit with a couple of transistors, MOSFETs, diodes, and LEDs thrown in, and it can show us some results if you need it. But to be honest, it's probably not that useful as you get into more complex circuits, but it is still better than having nothing at all. So I'll just run through again quickly how to set up the simulation, and then we'll have a look at some digital circuit simulation and what the differences, well, in my mind at least, between analog and digital circuits are. So I'm sharing my screen once again. And then also you should be seeing the EagleCAD landing screen. As always, usually I start with the opening up a schematic. And once again, schematic is just the symbolic representation of electrical circuits. I always first make sure that I'm working with the correct grid. And as I said previously, I like working with millimeters. And I like also showing the display. The next thing I like to do is to add in a frame. Search for my frame, press enter, and then place my frame at the origin. So it's at 0, 0. I can then center, zoom to fit my design, and now I am ready to work. As well, you will see that this frame is divided into A, B, C, D, 1, 2, 3, 4, 5, and 6. Why is it divided into that? Well, let's say I've got a circuit and somebody has got a comment on circuit, or I want to highlight a certain aspect of the circuit. I can tell whoever I'm talking to, look and square B2, which is this square here, and my circuit of interest is located there. So you can use these elements A, B, C, D, 1, 2, 3, 4, 5, 6 as reference to a certain location of your circuit. It just helps you as well to give reference if somebody wants to look at your circuit, or if you want to show them something in your circuit. As well, now we go back here to our add parts. Let's get back to our normal directory, our normal library directory. And the easiest thing for me is just to scroll down to my ngSpice library. ngSpice library, or ngSpice simulation. And here I have all my simulation elements. So I can start with a voltage source. Let's add in a couple of a capacitor. And add in some, oh, no, not design blocks. Add in some resistors. And then I can this together. It's very important to ensure that you are connecting your circuits and not just drawing a random line on the board. because sometimes a junction is created and sometimes it does not get created. You have to make sure that when you are drawing your circuits that everything is connected directly. Now, when we are creating our printed circuit board, there's other tests that we can run to make sure that our circuit is connected properly. But for now, just make sure that, or use the info button to check which nets are connected. And these are all connected brilliantly. I add in my values, so that's 100 ohms. That is 300 ohms. And that is 400 ohms, for instance. And this is a 100 microfarad capacitor. Now I can create my analog setup. I can have an AC value of, let's say, 12 volts, and it's a sinusoidal. Let's start with this. Let's create a transient function. It is a sinusoidal transient function with an offset of 0, meaning it starts at 0, an amplitude of 1. Let's create amplitude of 12, frequency 1, so it repeats every second. Let's make it repeat every 2 seconds, and then set value. So let's have a look at our simulation. Will give me an error. Why? Because I have no ground node. So I first close this, and I remember always when I'm simulating, add in a ground. So I merge this net, and now this whole net is 0. Simulate. Let's have a transient simulation for 5 seconds. Click on simulation, and then we'll see what is happening. So now we can see that the current in our circuit is reversing along with the voltage. We can add in some voltage probes. Add in some voltage probes, see what the voltage is there. Update my netlist. Simulate once again. And now we can see that the voltage is also, because it is an AC voltage, a sinusoidal AC voltage, it has this behavior like so. We can also change analog setup. We can also change sinusoidal to a exponential function. Now, I don't really use exponential at all. I mostly stick to sinusoidal, but you can play around with all these values yourself. And now what this does is I now have a sinusoidal function that changes the voltage, or as we can just go have a look at this, where it changes, the voltage changes direction. And as we said, it changes direction once or twice every second. So we can basically simulate AC signals as well, and also have a certain amount of voltage that we can check through our voltage probes throughout our circuit. So it's really, 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 really useful. Now, we are going to skip to, sorry, I'm just closing this function or that screen. Now we're going to move to digital circuits. So what are digital circuits and what are we going to be doing right now? Well, digital circuits are the AND, OR, and NOT gates. Let me just give a quick, I've got it here somewhere, not build and layout, right? No. Sorry, I'm just looking for something which I misplaced. Right, I'm going to be sharing my screen once again. And hopefully this is a little bit familiar to you if you have worked with digital circuits or you will work with digital circuits. So this is an example of a two input AND gate. So an AND gate, input A, input B. If both of them are a 0, output 0. If either one of them is a 1 or a 0, in this case 0, 1, 1, 0, they're all zeros. And I only have a 1 input when both of them are 1. Or when both inputs are 1. So we basically have the three basic gates is a AND gate, an OR gate, and a NOT gate. So we can also now simulate an AND gate, OR gate, or NOT gate. Now, I'm unsure of how far you go into digital circuits, or if you have done it, or you will possibly run into these, but you do get very complex digital circuits, which is a little bit hard to calculate. The good thing is we can now simulate these digital circuits. So let's start with simulating an AND gate. I'm sharing my screen once again, and I'll show you how to do this in EagleCAD. So we start with a new schematic. And I keep on doing this over and over again, just to reinforce that you should always, once you start a new schematic, ensure that you are working with the correct grid. So some people ask me quite often, why do I keep on doing this over and over again? Why just I don't save it as a setting? Well, it's because in the past I have made quite a number of mistakes when I used the incorrect grid size. And it becomes a little bit more important once we deal with the PCB board. But I find it's a good exercise to just set everything from the start always, because you get into a certain rhythm, and once you have done it, then you are sure that you actually have changed it to your grid and things that you are using. Because now in the schematic view, what we're working on now, it does not make that much of a difference if I work with millimeters or inches, because it's just a symbolic view. But once we move on to the PCB, where dimensions quite definitely do make a difference, I just like having my students in the habit of always checking and setting their grid sizes. So that's why I keep on doing this over and over again, just to have you in the right mindset that you always check and ensure that you're working with the correct grid sizes. So, and then we add in our frame. So the more you practice, the more this should all be, it's like your second nature. And then what do we do? Okay, well, we go back, we delete our search, we press enter again, and it returns us to our main library directories. We go to ngSpice once again, but now we go to ngSpice digital. And these are all the digital elements that we can use. So we have a 3-input AND gate, 3-input NAND gate, a 3-input NOR gate, 4 NAND, just a simple AND gate, an analog to digital bridge. So this, you would convert a voltage signal to a digital signal, a buffer, D-type flip-flop, if you're dealing with flip-flops, a source, a 4-output source, an 8-output source, a digital to analog bridge, another digital analog. So in this case, we had an analog to digital. Now we have a digital to analog 8-bit. We'll deal with that a little bit later. An inverter, a JK type flip-flop, a NAND gate, NOR gate, or a tri-state buffer, and also an exclusive OR gate, which we will most definitely use. Okay, but let's start with our AND gate. We select it. Let's just work in the middle. Now we have our AND gate and we have to set our inputs. This is where our digital source comes in. So we've got a choice between a single source, 4, or 8. So I usually just take 2 single sources, add in 1, add in 2, and these are now my sources. Now I can link them up. That's not very nice, does not matter. And then once I want to check the output, I just have to give my output gate, which I want to check, a little bit of a tail. So I just give it what I call a little bit of a digital tail, which I can then attach a voltage probe to. So I can attach a voltage probe to the output. I attach a voltage probe to my input and another one to the other. Then I can go to the digital source setup. Remember, we used the analog source setup. Now we have a digital source setup. And now I have to input certain times. So I'll fill them in and then I will talk about what these mean. 0, 1, 0, 1, 0. Okay, so I am just setting up a digital source. So pretty much like we set up a voltage source, now we are dealing with digital elements. So digital deals with binary, it's a 0 or a 1. Now in more like embedded systems programming, it'll most often be like a close to a 0 volt and a close to a 5 volt for 1. So the electrical system will give you a 0 and it will interpret it as a 0, or it will give you a 5 volts and that 5 volts will be indicated by a binary 1, depending on which system you're working with. If you're working with TTL transistors, you'll have a 0 and 5 volts. If you're working with CMOS systems, you have 0 between 3.3 volts, but it can be really be anything you want if you're working with a non-standard system. But just for the purposes of this exercise, we are dealing with zeros and ones. And if you're not sure what I'm talking about, a 0 is basically an open switch, and a 1 is where the switch is closed and voltage can flow, current can flow. And that's what I'm doing now. So I'm sharing my screen once again. I just want to show you. So I click on digital source setup. And I'm drawing in this gate here. So currently I'm setting up input number, well, actually input number B, to be honest, which is a 0, 1, 0, 1. So I'm telling it at time 0. So when the simulation starts, your output should be 0. At time 0.1 or 0.1 seconds, you should be a 1, 0.2, you should be 0, 0.3, you should be 1. Now, I can also probably, to make it a little more clearer, I can have this as seconds. So let's just have it as seconds. So at 0 seconds, it's a 0, 1, 1. At time 2 seconds, it's 0 and 3, 1. And then lastly, at 4, go back to 0. And I save my setup. Then I have to set up my other digital source. Also, time 0, 1, 2, 3, and time 4. and it should be 0, 0, 1, 1, 0. And I do this to mimic my output table here. So now I'm doing the A input 0, 0, 1, 1. So if all goes well, we'll have this type of output, but we'll have a look. So we'll save our setup. So what we have our digital gates, in this case, an AND gate. I have my digital inputs, which I set up manually. And now I have wherever I want to take my digital readings. So I can start my simulation. I have to take a transient simulation. It's already telling me that my stop time is 5 seconds, because that is up until where I have indicated in my digital source setup where you should be, where the simulation, for how long the simulation should start or take place for, and then I simply click on simulate. And now I have my outputs. So this is my input. It's 0, 1, 0, 1, and then back to 0. And my other input is 0 for 1 second, 0 for another second, 1 for 1 second, and then 1 for another second. And then according to our what we call truth table, it should be 0, another 0, another 0, and then 1 until my outputs change again. So now I have a simulation or a simulated result of an AND gate. Now, other elements, if we add in an inverter or a NOT gate, the logic inverter / NOT gate, we add it to the end. We connect it up. And we give it a little tail, which we can read. Add a voltage probe. So what's going to happen now? My gate, my AND gate, will feed its digital signal into the inverter. And then whatever digital signal my AND gate sends to my inverter gate, that is then being replaced or inverted. So when a 0 enters my inverter, it becomes a 1, and so on and so forth. So let's simulate. We update our netlist because we changed something in our circuit, and then we simulate it. And now we can see we have our NOT gate is at the top, and as you can see, it is an inverted version of our AND gate signal. Now we can also do the exact same thing for our OR gates. So just to complete our basics, let's remove our AND gates. We add in an OR gate. Now, it looks like these are connected. Let's see if they are connected. Yeah, it does. It did connect it automatically, although I didn't check it. I actually expected it to give me some sort of error. And we can see with the OR gate is that whenever either one of my inputs has got a high or a 1, it means that my output is a 1 as well. And then that input is then inverted through my NOT gate. And those are my simulation results. So when I was studying, this became quite confusing really quickly. And digital logic is relatively confusing. if you don't keep up and understand what is going on, then there will be a bit of a, you might get lost. So whenever I speak of a high or a 1, I mean the same thing. And when I'm speaking about a low or a 0, I'm also speaking about the same thing. Now, why do we do digital logic? Well, we build digital circuits. Your computer that you're looking at or looking at me at works on digital logic. And because all of our digital logic runs on 1s and 0s, we have specialized circuits that can help us with things that we want to like, that we would like to do. So I'm sure you're all aware of how a circuit does addition. We can have circuits do addition. Sorry, I'm just closing this, through a half adder and also a full adder. So we're first going to have a look at the half adder. I'm just going to be seeing if I have this. Yes. I'm sharing my screen shortly. So what we are going to be doing now is that I'm just going to show you some examples of useful digital circuits. So we'll have a look at creating a half adder circuit. That'll probably take us up to our break, and then we'll construct a full adder circuit. So what do these two circuits do is they basically add 2 bits together. They do addition, and then that addition is how your PC then creates or does addition, basically. So the half adder and then the full adder is what we actually use. And you might be required to create a similar digital circuit. So let's first just look at the half adder. I'm sharing my screen, and we will see a I might as well just place it on. Yeah, I'll place it in. I've just uploaded it into Teams, so you can have a look at while we're working through this. This is the. Does not help. This is the truth table for the half adder circuit. We have 2 inputs, A and B, and then our 2 outputs, sum and carry. So you have a sum, and the carry is if those 2 sums add up. When we're doing addition, if there is a carry or an overflow of a value, then that is then carried into the carry. So how does that usually work? Usually if you have, what we're not doing is we are basically adding 2 bits. So if you want to do 2-bit addition, you just need one of these devices. But if you are doing 4-bit or 8-bit, so basically what we're doing is we're adding in 2 bits first, and then the carry from these 2, from this addition, is then carried to the next one and next one. So we can chain these adders into adding up bigger and bigger numbers. But for now, we're not really going to do the addition or the chain addition, so to speak, because this is not a course about digital logic. This is a course about PCB design, and I'm just showing you the simulation potential of Eagle. And then we'll speak about the how we can then create a circuit or a PCB for our digital circuit. Right, so I'm sharing my screen once again. We'll have a look at the half adder, and then we'll create it in Eagle. Simple as that. So we have our truth table. We have 2 inputs, 2 outputs. The schematic looks like this, and the schematic realization looks like this. We've got an exclusive OR gate and an AND gate. So my sum is exclusive OR gate, and the carry is an AND gate. So let's do that. So we open up a new schematic. Once again, first thing we always do is make sure we are using the correct units. I add in my frame. I like my landscaped version. I add it at the origin where that little cross is. And then my next step is then navigating to the correct ngSpice digital library. ngSpice digital. So we are going to be using an exclusive OR gate and an AND gate. We are going to be having 2 inputs and 2 outputs. So we find one input and another input. We need to wire. Actually, let's rename our inputs to A, rename our inputs to B. So what I did, I clicked on the name button and then clicked on my specific gate that I wanted to rename. I then create a net. And then also this is fed into my AND gate at the bottom. Now they do not make connection, but we'll just create a junction. Now this is a little bit of a problem. Now I'm trying to connect these, and for some reason it does not want me to connect it. So, new plan. I delete all of these and I connect it directly to the input itself. So now I'm definitely sure that these are connected. I create little digital tails. So what do I need? I need to have a voltage probe for the input, voltage probe for the other input, a voltage probe for my sum, and a voltage probe for my carry. Now I can also give these names. Let's give these, let's give it a value. So let's name this one the sum, and this is the carry. This net is my A net, and this net is my B net. So now I've got a good idea of what is going on. The next thing I need to do is set up my digital sources. And pretty much the same way that we've done it before. Let's just create the time. So run up until, 0, 1, 2, 3. This will be 0, 1, 0, 1. And this is according to this table right here. Save setup and do the exact same thing, setting up my source B. 0, 1, 2, and the 3. This will be 0, 0, 1, 1. And that is according to my B truth table. So I save my setup once again. I click on simulate. Once again, transient. Let's keep it at 5 or at 4 seconds. Update netlist and simulate. So this is my simulated circuit. So purple is my A. This turquoise color is B. This is my carry, and this is my sum. So this makes a lot of sense. This is exactly the same as what we have in our half adder truth table. So my half adder A 0, 0, 0, 1, 0, 1, perfect. 0, 0, 1, 1. Yes, my sum, which is my red line, is 0, 1, 1, and then 0, and my carry is 0, 0, 0, and then 1. Perfect. So we have simulated a relatively simple digital circuit. Now, a half adder circuit is not that difficult, and I'm sure if you do have a little bit more experience with digital circuits, it'll become really difficult really quickly. So I'll just show a relatively difficult example of a digital circuit before we move on to creating a full adder circuit. Yes, okay, so no, I don't want to do that. I know you're watching me doing something. So let's just have a look at a relatively complex circuit. Because now, a lot of the time people say, oh, well, that's relatively simple. I mean, I can kind of work out in my head what the values are. But a lot of the times you have these cascaded, very complex digital circuits, and it's not always as easy to see what the values are. So I'm sharing my screen once again. As always, we create a schematic. I check that my grid is the grid that I want to work with. And once again, I like using millimeters. I add in my frame. And that's the frame I like. I place it at the origin. And then I can go directly to my ngSpice digital library. ngSpice digital. I can have a 3 input AND gate. Let's have a couple of them. A NAND gate. And an OR gate. All hooked up to a 5 input NAND gate. So how are we going to connecting the circuits? I'm working off a little sheet that I have. And how many? 1, 2, 3, 4, 5, 6, 7, 8. We've got our 8 input source. And almost done with this relatively complex circuit. And I have one digital output tail. So now, once again, I have to set up my digital source. And if I enlarge this, I have all my digital elements. So let's start at time 0, 1, 2, 3, 4, 5. No, that was 7, 8, 9, 10, 11. Nope, I was wrong. 13 and 14. So I am not adding in any usual digital patterns. I am operating on the assumption that I have got a certain amount of digital readings that I want to check. And I want to prove just a little point. Now, I know it's not a lot of fun watching me just input random numbers, but at the end of it, I believe it will be kind of like worth it. And I'm almost done. Make a lot of sense. Oh, that's a so I've now created all of my inputs. I've saved my setup. I create my digital probe here at the output. I can have all of my inputs also as digital probes, so I can see what my inputs and outputs are. I've gotten one right here. Yes. And I can simulate. I think we go up to about 16 seconds. Update my netlist, simulate. So now we come to a very important part. There is an error. So now too few parameters of subscript type NAND 5. So, aha. So the simulation has given me an error. Perfect. I love it when I've got errors because then I can explain something of what went wrong. And we'll have a short 5-minute break. And then we'll discuss what went wrong in my very complex simulation. Right. 5-minute break, drink some water, do what you need to do as we head into the last session of today's class. Very short 5-minute break. Now, to start where we left off last time, I just want to recreate the same things that happened. I'm sharing my screen again. So I received this error. There was an issue running simulation. See simulation output for more detail. So I press OK, and it goes to output, and it tells me there are too few parameters for subscript type NAND 5 in terms of XX6. So this is the component I'm looking for where the error is. So let's see to view parameters. Let's have a look. Like, yes, I forgot to add one input. So I will then have to connect this input with, I think, actually directly this input there. So now we have everything connected. Now we can run this simulation again. Transit, 16 seconds, update my netlist, make sure that everything is at the most current state. I simulate again. And now I have this simulation, which is pretty hard to understand. So let's first have a look and see. So I'm actually looking at, okay, so let's rename this just to have a better idea of what is going on. So let's call this output. Run a simulator again, update my netlist, simulate everything again. And then I can have my red line is my output. And as you can see, it is pretty much always 1, except very, very few elements there. It is pretty much always 1. And that is because I have got a NAND gate, and a NAND gate is an interesting type of gate because it is the opposite of an AND gate. So whenever, the only real time where it will be a 0 is when all of my inputs are actually 1, then it should be a 0. But at no one single time are all my inputs 1, so my output is never ever 0. So this, I'm using this example as an illustration that these are sometimes it is not really easy to see the output of these circuits, but when you simulate them, the outputs become a little more clearer. I can also add in different elements here or different voltage probes between my gates, and that just helps me to get a better idea of what is happening with my digital circuit. Now, you might be asking, okay, great, I can now simulate digital circuits, but what has that got to do with PCB design? Well, because you can actually build digital circuits out of a circuit or a digital circuit itself on a printed circuit board. Now you do get integrated circuits. Oh, I'm sharing my screen. Sorry about that. Let's create a new schematic. First of all, do everything I need to do to be able to use it correctly. And then add in a frame. As you can see, I always do this. So let's search for an AND. Now my search brings up a lot of these different elements, and I would like to highlight the 74 version of integrated circuits. So what does that mean? That is usually when you have an integrated circuit, i.e. a chip, usually the identification numbers, these start with 74 and then will have a certain identifying number. Now these are TTL circuits, meaning that they operate between 0 and 5 volts, meaning a digital 0, logic 0, or a low value, whichever you want to call it, is very close to a 0 volts, and a digital high value is very close to 5 volts. Now, they're not exactly 5 and 0 because there are certain ranges in which they operate, but we're not going to get into that. But we will have a look at how to design a digital circuit now for a PC to be implemented on a PCB. So I worked with these quite a lot when I was studying. And you can see that this 7408 is a quad 2 input AND gate. So the schematically, it is represented like so. It's got 4 different AND gates, and in the footprint looks an IC like this. It's a dual inline 14 package, meaning it's got 2 parallel lines of pins, and there are 14 in total. So 7 on the one side, 7 on the other side, and we have 4 AND gates. So let's just select this one, see what it looks like. So it'll usually give me the ability then to select select our 4 AND gates, and then I can create them as I want. They've got dual ones, triple AND gates, triple inputs, and pretty much any type of logical circuit you can think of, you can create with this software, or the component would be somewhere in a library. So this, I keep on getting back to, so like what we're dealing with now, we're dealing with the prototype elements, or the prototype in our cycle in circuit designing, or in projects, where we have a simulation, and once we have our simulated circuit, we can now produce our real circuit and then implement those values in a PCB design or in a breadboard design. So especially now with, well, not especially with analog or digital circuits, we can create the circuit in an online environment or in EagleCAD, simulate the results, make sure that we have the results we are looking for, and then from there we create the physical circuits ourselves. So that is why I'm showing you, and that's we are slowly building up to the last step of prototyping, and that is creating the PCB itself and then testing the PCB itself. So while on the break, I realized something, that I did not give you the correct information about the half adder circuit. So the half adder circuit, we have 2 inputs, 2 outputs. So the inputs are 2 bits, 1 individual bit with another individual bit added together through an exclusive OR gate, and we can see the sum of those 2 bits being added, and also the carry of those 2 bits being ordered. Then I said, well, we can link these up together to add in more bits, but that is not correct. You cannot do that with a half adder because you have only 2 inputs. So where is the additional bit gonna go? So this now means that I made a mistake, and we are now going to be looking at something called a full adder. So I'm adding in another another picture of a full adder circuit with a, so make sure it's the correct. Yes, it is the correct. Just want to get into place, but I can drag and drop it. Right. So if you want to add up more than just the 2 bits by using the carry, we implement a circuit called the full adder circuit, which I've just posted on inside of Teams chat. Now, at the end of this class, I will send an email. I'll send 2 emails. One email is the link for the next week's class on Monday, and another email will contain a couple of attachments. Excuse me. One will be the attachment for the transistor and the switching LED circuit. Another will be the half adder circuit and the full adder circuit. And then I would ask you to just go and practice these circuits in simulation. Create them in simulated environment or recreate what I have just done. And if you can do these 2 or 3 examples, then that is what I expect you to do within in terms of simulated circuits for this course. So let's have a look at the, let me just close this. Let's have a look at creating a full adder circuit. So I'm sharing this once again, my screen. Right. So once again, we are creating this circuit here. I don't know why it's got a black background. I do not understand why. Maybe I can change it. No, it does not matter. I'll create the circuit any case now in in Eagle, and then I'll send that to you as well, so it's a little bit more clearer on my white background. Okay, so what we always do, it's getting boring at this stage, but it's necessary. Set up my grid, make sure that my grid is exactly the grid that I would like to use. It's displayed. Next step, as we always do, is add in the frame. And add in my frame like so. The next step is finding the specific elements that I would need. So I delete those search results. I go back to my ngSpice digital elements, and then I have a look at, I have 2 exclusive OR gates, 2 AND gates, and an OR gate. So that is what I'm looking for, 2 exclusive OR gates. 1, 2, 2 AND gates. 2 AND gates. Well, let me just, and an OR gate. Right, so that is the gates. So once again, this means this line in the black means an exclusive OR gate. I have 2 of them, 2 AND gates and an OR gate at the back. So let's just rearrange so that we have got a better understanding. So I press escape. I do not need that. So I'm going to delete it. Oh, it's gone. Great. Move my gates around like I need them. These 2 are going to be cross each other like this. These 2 OR gates are feeding into each other like so. And now we can connect up our gates. Well, let's just add in the 3 inputs. So I have 3 distinct inputs. Let's have 1, 2, and 3. and we can connect these up. Let's just rename all of our inputs. So we rename this is our A, this is our B, and then this is our C in, or the carry in from the previous elements. So now we can connect everything up. So this is what I'm doing, the connection. Now, this is usually where the biggest mistakes happen, is the connection. Just be aware where you're connecting what and what goes to which connection. This feeds into this gate. Now it looks very chaotic. I am sure that it does. But once we have connected everything, everything will make a little bit more sense. These two are connected. We have two outputs, so we have two output tails. We connect a digital output on these two tails and digital outputs on all of our inputs, so we can read them and make sure that our our full adder circuit is working correctly. Let's just relabel everything. Oops. Name A, B, C in, and this will be our sum. And C out, or our carry out. Now we will have to create or set up our digital sources. And once again, let's keep with seconds. 3, 4, 5, 6, 7. This will be 0, 1, 0, 1, 0, 1, 0, 1. And how do I know that it's 0, 1, 0, 1? I look at the truth table. Okay, well, I'll switch these around in a second. Don't worry about it. Okay, well, let's just stick to what this truth table is telling us. So let's change all of this. So that is A. B is 0, 0, 1, 1, 0, 0, 1, 1. Let's set up this digital source. Once again, making sure that the time is exactly the same. 6, 7, 0, 0, 1, 1, 0, 0, 1, 1. And then our last source, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 0, 1, 0, 1, 0, 1. So now I have created my sources according to the correct inputs. Now, if we run the simulation, we should see these sum and carry outputs. Now, did I forget anything? Hopefully not. Let's run our simulation. Transient, we don't need 16. We only need 7 seconds because that's the amount of inputs that we have. Well, let's do 8. Why not do 8? Update my netlist and simulate. So what is happening? Let's just add in our full adder circuit. VA is purple. That reacts as I would expect. VB is blue. And CIN is green. Excuse me. And my C out, the carry out, is 0, 0, 0, 1, 0, and then 3 ones. And my sum is 0, 1, 1, 0, 1, 0, 0, 1. Now, you might be wondering, what are these little peaks here? Why does it have this little spike? Well, it's a peculiar thing. I have to explain this because this is a little bit difficult to understand. It is because we are dealing with digital values, and we also like dealing with the ideal digital values, meaning there is no build-up time between a 0 and 1. A value is either 0 or 1. So in reality, a voltage would take a little bit of time to build up to its maximum level. And it does take microseconds, sure, but it does build up a little bit. But in terms of our circuit, is an ideal circuit. So at the space where circuit 0 to a 1, at that split second, at that time frame, it is still actually considered as a 1. And I'll show you what I mean by that right now. So let's have a look at this element here. So here we have sort of like the high and the low, but on the exact same time element, it is a high and a low. It is a little bit difficult to understand. So let's run the simulation again and see if it happens exact same way. It does. I want to show you something else. Let's change it to 2.5 seconds. I want to just zoom in on that one signal. So what happens here? Let's add in the other signals. So what happens here is at this specific time frame, our circuit is at the same time a high and also a low, meaning that our circuit, our output is unsure if it's receiving a high or a low, because at that very specific time frame, it's both a high and a low. Now, this is just really a timing and simulation issue. But it might highlight an issue that you might have in your circuit as well, is the timing element. So this is why simulation is also a relatively good thing, because it can show us at that very specific point in time, our circuit does not really know if it's a high or a low. So to mitigate that, we can have either add in certain circuit or certain elements to make sure that it goes from a 1 to a 0 in a more gradual way, or we have certain safeguards in place that can help us prevent that element from happening. But it is something that you'll have to deal with, but just the simulation results can now show us that there might be a little bit of a problem there. But then again, I'm not exactly here to give a class about digital circuits. What I am here to do is just to tell you that you can have digital circuits simulated within EagleCAD and then use that simulation results to validate the circuit that you have created, and also then use those results to create a circuit with real ICs. So if you want to create a, how much does actually do that? If you want to create a digital circuit that works as a full adder, that is actually a pretty good idea to do in the next class. Oh, this is going to make a note. Sorry. So what I am going to do is I am going to, hopefully in the next class, when we go to the PCB design, I will create a full adder circuit and then transfer that to a PCB design, order the components or the PCB, and hopefully it should be coming here before the course ends, and then I can show you the circuit, add in all the components, and then also show you the operation, and then sort of like we can talk about the design process that we went through to get there. It's actually a good idea. I've been looking for an example that I can use, and it looks like the full adder is a circuit that I can definitely use. So that being beside the point, we are getting to the end of this lesson. We basically had a class about simulation of analog and digital circuits. Now I'm fully aware that these are not the best. It's not the best simulation software that you can have. It is very limited in what it can do, but it can still do certain useful elements. And it can still form a part of you creating circuits, validating them through software, and then using the software to create your final product. And this is what this course is all about. It's taking you through the process of creating circuits, creating the physical representation of that circuit, and then producing that circuit, and then testing that circuit at the end. And that is what we are all hopefully going to be doing with all of this. So it's going to be lots of fun with this. So in the next class, which is on Monday, we will start, I think I will start with creating a full adder circuit, transferring that from the schematic design, which we've done the simulation on, that to the PCB, and then creating a PCB, sending it off to a manufacturer. So that should all happen on Monday. Yes, it should work. So that's the next step in our evolution of what we're going to be doing. We're going to be taking our schematic designs to the PCB, and then having a look and discussing about what a PCB is and how we can create easier elements for that PCB. And we'll talk about what you need for physical circuits and what you need to think about for physical circuits. And one of those things we need to think about, if we create our circuit, we have to think about how are we powering our circuits. How are we delivering the power to our circuits? Because we have all just designed circuits. We've just added in a voltage source, and that is fine. But that voltage or that power needs to come from somewhere. And that usually is also where we add in connectors, batteries, sources, and all that kind of thing. And we will talk about all of this stuff in the next class. Right, what else do we need to cover for today? We've basically done the simulation that I would introduce to you. Now, we will not go more in depth into the simulation process because quite honestly, this whole course can be just about simulation, but we're not going to do that. We're going to moving on to the physical circuits. Now, I do not give homework. I do not expect you to hand in a report about the circuits that I would like you to have created, but I will be emailing 3 schematic designs for you to hopefully implement in EagleCAD. So the one is the circuit with the flickering LEDs. So I would like you to go into EagleCAD, create a simulation, an analog simulation by using the NG Spice elements, creating a circuit and then simulating the results just like I did here. And then I would also like you to create a half adder and then a full adder digital circuit, simulate the results and understand how that works. Now, like I said, this is not a homework assignment. I do not expect you to hand this back in as a report, but I do expect you to put in some practice and use the software by creating some simulations so that everything we have done up until this point, you understand. If you have major problems and you cannot do this, then let me know, and then I will figure out how to get you up to speed and how that I can prepare you to pass this course, and more importantly, prepare you to understand the knowledge that I want you to have. So I'll be sending an email, or 2 emails, as I said before. One is the invitation for the next class. The other email will be the the unofficial homework email, where I would have those 3 elements or those 3 circuits design and simulate for me in attached to them. Like I said, I will not expect you to hand back a report, but I do expect you to complete this and to be able to simulate or construct and then simulate those circuits. And like I said, that is what I expect you to be able to do up until this point. As well, go through the PDF of the presentation that I sent you, because those elements that we went through, I probably will not be repeating again, because I fully expect you to understand what we went through, and due to the fact that there has been no questions up until this point, I expect that you understand everything that is going on. But to that end, you are still free to ask me any question that you might have. If you do not understand the way that I'm speaking, let me know. If you do not understand certain words that I use frequently, let me know. If you cannot see the circuits I'm creating, either the white background or the black background is bad, let me know. If somebody doesn't tell me, then I'll just carry on as usual. And right, I think that is it for today. I'm not going to be starting a new circuit right now. Like I said, I'll be sending you the 2 emails with the homework and with the link for the next class. And then looking forward in the next class that I will create the PCB of a full adder and hopefully have it sent out to a person to be made. I wish that you all have a very good evening, have a very good weekend, and then I'll see you all on Monday. Thank you for listening, and see you next time. Bye, everybody.